Hello.
Hi, good morning.
Good morning.
Go ahead, Janvi.
Good morning, everyone. Welcome to the KRVIA Encounters. Today we have Saurabh Mhatre as our speaker. Saurabh is a creative technologist and an architectural designer whose innovation work span across various domains, including architecture, product design, engineering, and material science. He has worked on transdisciplinary projects dealing with the 3D printing of ceramic and concrete, deployable mechanisms, smart materials, and folding robots in collaboration with Harvard School of Engineering, Wyss Institute of Biological Engineering, and the Autodesk Build Space. We welcome you, Saurabh. Now you may start with the presentation. Thank you.
Thank you so much for inviting me, and thank you everyone for getting up at 8 a.m. and we're still having like a really good full house. Let me start my presentation. Yeah, can you see my screen?
Yes.
Okay. So, hi, I'm Saurabh Mhatre. I'm a senior research associate at the Material Processes and Systems Group at the Harvard Graduate School of Design and the Harvard Center for Green Buildings and Cities. I'm trained as an architect, but currently place myself in between the fields of design, engineering, science, and art. I'm going to start with sharing some important moments in my journey with you to give you a context of where I come from and what has led me to do what I do. All throughout high school, I was studying to be a computer engineer, but at the end, I decided to make a switch to architecture. Wanting to go into a creative field is something I was always leaning towards, and I was a tiny bit influenced by my dad and sister, who are also architects. Doing my bachelor's in architecture in Mumbai, I was exposed to both analog and digital methods of designing and making, but was still quite constrained as the integration of fabrication techniques and computational design at that time were not yet established there in Mumbai. I became very interested in parametric design and design computation and hence decided to do a master's. I did my master's in design technology, a design research based program at the Harvard School of Design. This program exposed me to emerging technologies, robotics, material science, design thinking, etc., and taught me about designing at various scales from nano to micro to macro. One of the most important things I learned being in this ecosystem of the university was the importance of collaboration and transdisciplinary design. There is a novelty in the solutions and opportunities that arise when architects, designers, engineers, material scientists, doctors, people from different fields collaborate with each other towards a common goal. The challenges of our time demand rigorous and socially robust knowledge of different fields. Research cannot be done by just one person. We build on the work done by others before us, and we collaborate with people around us. Before I dive in, I would like to highlight that I have been fortunate enough to get a chance to work with an amazing group of people with varied backgrounds, not just from the Graduate School of Design, but also the School of Engineering and different other research groups at Harvard CEAS, the Wyss Institute, and others in the Boston ecosystem during my 8 years in the university. The work that I'm going to show you is a collaborative effort between me and all of these amazing people. Throughout my presentation, you're going to see this symbol a lot, the symbol in red. In chemistry, it denotes a system or a process in dynamic equilibrium. There is constant back and forth exchange of information among both the entities on either sides. This will be manifested in the project examples I'm going to share with you. You will also see an interesting dialogue and dynamic shifting between curiosity-based research and applied research. where we give ourselves the freedom to explore as well as focus on solutions to a very well-defined problem. I'm going to give you 3 examples of projects which fall within the blurred domains of design, science, technology, materiality, and in some way contribute to the larger agenda of sustainability. First, I'm going to talk about our work on 3D printing of ceramic, a sustainable and opportunity-driven way of scaling up 3D printing in context to architecture. And then I'm going to show you 2 projects, one which starts off as pure curiosity-based research, a project which is a solution trying to find a problem, and the other one, applied research, which is a solution for a very well-defined problem. Due to time constraints, I won't be going too much in depth, but will be open for questions after the presentation. I'll start with the first one. Why ceramic 3D printing? 3D printing, also known as additive manufacturing, is a manufacturing process where a 3D printer creates three-dimensional objects by depositing material layer by layer in accordance to the object's digital model. Using these 3D printers, we can make efficient, precise, dynamic, and beautiful creations with a variety of materials. Majority of the 3D printers available in the market cater to the desktop scale and use commonly available plastics as the printing material. But when we think about 3D printing of larger objects like buildings, we can't imagine printing tons and tons of plastic. It is not sustainable, and hence materials like ceramic and concrete come to mind. Majority of the large architectural scale 3D printers are 3D printing concrete. But we believe that ceramic as a material holds a lot of promise as a sustainable option, and when paired with robotic workflows can drastically reduce the carbon footprint caused by the construction industry. I would categorize this into an opportunity-based research. For the last 5 years, we, the MaP+S group at Harvard GSD, have focused on studying conventional ceramic manufacturing and forming processes and researching on how integration of emerging technologies can add novelty to the industry, but also achieve larger goals like customization and sustainability. I'm going to focus on 2 projects, one which looks at the 3D printing of a single body of clay, and another where we are co-extruding 2 different bodies of clay together. This project utilizes a clay extrusion system and 3-axis armature to produce each of 552 unique ceramic elements for the pavilion to be exhibited in Sevizama, one of the biggest ceramic expo in Valencia, Spain. Each element is sized according to its position within the structure, the dimensional constraints of the printing bed, and a maximum allowable tool path length. We developed a novel computational approach to generate the surface geometry of the pavilion, discretize the form into individual bricks, and accommodate for the structural metal frame. Toolpath geometry and machine code is also generated directly within the parametric model. The digital workflow enabled us to account for shrinkage during the drying and firing process, reduce overall printing time and material consumption, and tune the stability of the individual bricks. Here are some shots of the pavilion. The outside surface was smooth and the inside surface was bumpy based on research on geometry and thermodynamic heat transfer of the different surfaces. This project shows that using CNC and robotic technologies with ceramic enables the vision of mass customization rather than mass production. In this project, all the material testing, workflow development, and prototyping was done in-house at the university in collaboration with the Harvard Ceramics Lab, and the knowledge was shared with the Institute of Ceramic Technology in Spain, who did the final production. After having developed a workflow for the efficient printing of a clay body, we wanted to see what opportunities arise when we are able to print multiple clay bodies in a monolithic form. Is it possible to print different clay bodies with different mechanical performative properties in a single module? Can we imagine our walls to have a single material, ceramic, but performing differently across the cross-section, certain areas taking load, certain areas offering thermal insulation, areas being porous and super light, all within one single homogeneous form. That's what we explored in Project Janus. Janus is defined as the god of transitions and duality in ancient Rome and hence seemed like an apt name for the project. Throughout the process, we always look at examples from different fields as a start point. In this case, you can see that the method of extrusion has been quite mastered in the food industry for the manufacturing of a lot of commonly known food items. The same is also well developed in the polymer extrusion industry and academia, especially the design of multiple hierarchies of coaxial nozzles. We thought, wouldn't it be interesting to do the same with ceramic? What design and application opportunities would it open up if we're able to achieve a multi-material 3D printed ceramic workflow? So building on a previous work, our setup consisted of two tubes of different bodies of clay, red and white as seen, with similar shrinkage and water absorption properties, filled in tubes of a screw extruder, which is like a large syringe mounted on top of a 6-axis robotic arm. Normally, this robotic arm is used in fabrication processes like assembling cars, but for us, it's a very flexible form of tooling. The two material tubes were aligned in an angle of 45 degrees as it reduces the length of travel from the individual cylinders to the nozzle, as well as increases the travel length after the point of intersection to counter the material stresses. Ceramic as a material goes through shrinkage in multiple phases, from its first stage of printing to its final stage of firing. That's why it's very important to select the two bodies with similar shrinkage rate and water absorption. The design of the nozzle played a very important role in our process. After a few iterations, we narrowed down to two designs. First, the Janus nozzle, which could print the two materials side by side, and the center core nozzle, which will print one material inside another. Both had a lot of potential in design, as they could offer different affordances for the product, but for this project, we decided to focus on the Janus nozzle because there was more design space to be explored with it, given the degrees of freedom of the robot it would be mounted on. In simpler terms, when you look at the Z axis, if you rotate the Janus nozzle around the axis, it gives you more unique possibilities than the other. This is how the extrudate, the material that comes out of the nozzle, will look like for both these cases. Using the Janus nozzle, multiple tests were performed to explore the design space, to establish relationship between various parameters of extrusion like robot speed, layer height, bead width, extrusion rate. We tested different dimensions from lines to surfaces to solids. Once we got a hang of the parameters, we started testing them on flat toolpath objects. Using these objects, we also started testing the different relationships between the parameters. For example, keeping all the parameters constant, increase in the robot speed reduces the width of the printed bead, and hence decreasing the robot speed increases the width of the bead. So in the right image, you can see that by adding slight increments to the robot speed, we got a decrease in the bead size. And because of the geometry, there was an increase in the level of porosity of the tile. We also experimented with three-dimensional objects where the toolpath was static and the nozzle orientation was dynamic. As well as 3D forms. Our computational workflow used a plugin called Machina, developed by one of our team members, Jose Luis, to go from digital geometry to the robot code to the printed object. Based on the rotation of the fourth axis, we were able to accurately determine the deposition of a particular material where we wanted it. This helped us to know exactly the effect the angle of the extruder of the robot would have on the printed path, as well as the path, how it would look from top as well as side elevation. Knowing this, we decided to create a proof of concept of our research. To be able to take in input a black and white image, and the script would divide the image into horizontal tool paths. The rotation of the tool of the nozzle 180 degrees at the fringe of the black and white pixels was like the main agenda. So as you can see in layer number 45, there at the intersection of where the white pixels change to the black pixels, there would be a change in the fourth axis of to 180 degrees, and hence it would cause a change in the body of clay that's visible in the front elevation. Here's a video of the process. I guess you get the idea. And here are the fired versions of the printed tiles. For us, the two different colored bodies of ceramic were just placeholders to develop a workflow to print two materials together. In some of our current work, we have one body of clay with high mechanical strength in order to take loads, and another body, a porous and lightweight ceramic foam, to act as insulation, printed in the same brick. Hence, instead of using a lot of different kinds of materials in a typical wall section of our houses, which perform different functions, we can envision a single material, ceramic, with variable properties to do the same. The next project I'm going to talk about is KRVIA. This project falls in the curiosity-based, opportunity-based research domain and is a solution looking for an application. I'm going to start off by highlighting the differences between rigid and compliant mechanisms. Rigid mechanisms, what you see on the left, require a lot of parts, are complex to assemble and prone to wear and failure. Compliant mechanisms, on the other hand, are lightweight, low cost, easy to assemble, and require minimum actuation. KRVIA is a patented system that uses material elasticity and geometry to go from flat to 3D with minimal actuation. This mechanism leverages buckling, which is conventionally something you avoid in structures and construction for its deployment. It is different from bending by the direction of the force applied. KRVIA is manufactured out of flat sheets of elastic material with simple fabrication techniques. It is fast to assemble and requires minimal hardware, making it cheap to manufacture. It can be divided into two types based on the method of actuation. One from the perimeter, the outside, and the other from the inside in the center. With the help of a parametric model, we have control to change all the essential parameters of the geometry from the diameter of the mechanism to number of pins, width, etc. Our developed parametric model makes the system applicable to a wide range of scales from small medical devices to larger furniture and structures. The system is suitable anywhere fast and compact deployment is needed, as in the following examples. We have successfully developed KRVIA at the millimeter scale in collaboration with the Harvard Microrobotics Lab. KRVIA can be integrated in optical devices with moving parts, such as lenses and diaphragms. Its aesthetic qualities are also suitable for the design of household products, such as lampshades and lighting fixtures, where the intricacy of the geometry creates interesting patterns both as a static object or even better, as a dynamic one. The compliant transformation of the system can be used to modulate the intensity of light. Freeform is suitable for furniture designs that can be shipped flat and deployed very fast by anyone with little effort and no tools. The method of fabrication is dependent on the scale, which in turn determines the thickness of the material used. It's compact to store and transport, easy to deploy. Geometry facilitates the creation of functional and affordable products, while at the same time providing minimal and elegant design aesthetics. As you can see from the above examples, different scales of this mechanism can be manufactured from different materials and different processes. Some fabrication processes make sense at certain scales. As a side note, we also have a very good agreement between our experiments and simulations, which I decided to keep on the backstage of the presentation. Those interested can check out the paper we have published in Advanced Functional Materials along with the Harvard School of Engineering. There's a research group there called Baltodi group, which also helped us quite a bit to develop all the mechanics side of this. In conclusion, KRVIA is a technology with high parametric flexibility to cater to applications at various scales where rapid deployment is essential. Again, this work would not have been possible if it weren't for all of these various people from different groups at Harvard. Okay, now moving on to the third project. So, as we all know, the pandemic has been the most dramatic disruption to human activity in a generation. For many designers, it has been a time to refocus and rethink how we design products and how, as designers, we can use our skills for the greater good. For our project, Apollo Isolation Hood, our problem was very well defined, creating a barrier to separate the doctor and the suspected COVID positive patient to reduce the aerosol spread of COVID. The Apollo Patient Isolation Hood is a localized negative pressure ventilation system for hospital beds to help contain the droplet spread of COVID, including during aerosol generating medical procedures such as intubation and extubation. The, the patient isolation hood encloses a patient's upper torso and head in a negative pressure environment. It provides a barrier protection between the doctor and patient and controls the aerosol via negative pressure environment. This is a collaboration between the Harvard School of Design, Mass General COVID Innovation Center, Boston Children's Hospital, and other industrial partners. In our meetings, the doctors from MGH and Boston Children's Hospital provided us with 36 guidelines to design the hood and their weighing as per priority. Some of the guidelines range from optical clarity, the surface smoothness, that it should be very lightweight, very flexible, it can adapt to different bed size, etc. As a group, we looked into multiple options of enclosures which would be deployable and easy to manufacture. Because of the severity of the pandemic, we were on a very strict timeline and wanted to look at forms which were easy to fabricate and very easy to assemble with minimal effort. That's why we started to look at techniques of origami, kirigami, and active bending. The technique of creating volumes from flat sheets. As we were in lockdown and had lost access to the physical fabrication lab, we started by simple paper and knives to make small prototypes of our designs, while also speculating the material and processes needed for manufacture of full-scale ones. Can you hear me fine?
Yes.
Okay. Simple origami techniques were a good start and could easily be scaled up using thin sheets of PETG plastic. One drawback with origami was that it was accompanied by edges and creases. Hence, to omit the edges and get optical clarity, we started bending instead of folding. So, every well-defined edge became a smooth bent surface. The plastic needed to be thin enough to fold and bend, but stiff enough to keep shape and not wobble. The bending and locking also added a lot of structural stability to the forms. Here is one of the first versions of the hood we designed. I'll use this to explain how it folds. As you can see, there's an overlap of the two flaps which give it a sort of double thick surface. You can see a assembly of a miniature scale version of the hood. Seeing potential of this design, we decided to make a full scale version of the same with PETG plastic. The best aspect of these forms was that they were made up of a single flat sheet and needed minimal joinery. And we had the doctors from the hospitals test this in the hospital, and we also did a lot of tests of this form in a lab. Over the next few days, we prototyped through a lot of different iterations, taking into account the guidelines, stability tests, and the feedback from the doctors. Some of these stood out as viable options which satisfied most of the critical guidelines highlighted in the start. They did have some demerits though. Looking at the pros of the most promising options, we designed the final hood which had the best parts of the above options and none of the demerits. So we came to the final design, what we call is the Apollo 3. This shows a quick video of the fabrication and assembly. It can be cut out of a thick PETG sheet in less than 20 minutes and assembled under 1 minute with minimal joinery. We were able to use a thinner material in the Apollo 3, and by some overlapping, like the overlapping of the geometry, we give a double thickness layered wall where the most strength was needed, which was at the back. Here are some detailed shots of the hood. The Apollo 3 was made up of a flat sheet, easy to manufacture, had minimal joinery and assembly, was lightweight, was compliant to cater to various body types, optically clear and stackable. We made 3 final prototypes in-house for the start and 20 more later after approvals and sent them to Mass General Hospital, MGH. And 50 more were manufactured after by a teammate who formed a company for the same. Design is an iterative process. There's a lot of back and forth. Here we see what I call the process prototype feedback loop. Prototyping at different scales informed each other, and they were constantly informed from the feedback given to us from our colleagues and who are from different fields. Communication and teamwork is a very important part of the process. Due to material scarcity and supply chain issues, we had to be very mindful of the plastics we used. PETG was in short supply and most of it was being used to make face shields. Minor changes were done directly on the full-scale models, and major changes were first tried and tested on the smaller models before translation to full scale. This was a collaborative, non-hierarchical effort of more than 200 people, possible using online communication via Slack. Designers, engineers, and doctors and industry partners took active part in this whole process. All files have been made open source via GitHub to help disseminate this knowledge to anyone out there. It started under strict fabrication constraints under the COVID lockdown, was translated into a full-scale prototype with the constant feedback from doctors and other designers, was tested at Mass General Hospital, and now is currently on display at the Cooper Hewitt Smithsonian Design Museum in New York as part of the Design and Healing Creative Response to the Epidemics exhibit till Feb. Basically, this is the last month of the exhibit. And that is the end of my talk. I hope I did not go too fast, and yep, I am open to questions and comments.
Yeah. Hi, Saurabh. Very interesting presentation, first of all. And I must say your lab is very inviting. Yeah, I wanted to, on behalf of the students, or probably also what we want to know been doing. We've been lately started with the basics of digital fabrication right at the college. I've got a couple of printers and planning to get CNC cutters and everything. I think the prime thing for students at least to understand is how do you translate your design and how do you foresee it before manufacturing that this could be done, because if that is something we can sort of perceive and plan. I think, and the most advantage that it offers that you already have probably two hands or one hand extra working for the model for the final prototype, and you don't have to worry for it. If you could at least for academia or for students, if you could explain that. The other point was the first project you showed and the second one, key form. I think the patterns of spirograph that you generated from Grasshopper. Uh, the tech you used was probably laser cutting, but I mean, what if it's anyway a flexible material? So could you also have, or are you all planning to do an additive manufacturing of it, such that you could actually 3D print a flex material or a TPU and then generate the same form, and probably that would give you even more options. So did you, is it a thought or is it possible or what is it?
So I'll start by answering your first question. So I think whenever we sort of start a project, like for us, it's always like we always start by making, right? Like, so it's always us, even though we have a lot of these different fabrication capabilities available to us, we always start with the most basic of creating analog hand models. Like just trying to see what material, what thicknesses, what works first, what are the possibilities that working with this particular material of this one thickness can provide to us. But just a lot of analog tests, we give ourselves like a sort of like a certain phase of freedom to just go wild, trying out a lot of different things. And this, like just playing with the material, informs us a lot about what the limitations are or what the opportunities that this materials could be offering. Then again, once we are in the divergent phase of trying out a lot of things, then we have these ideation sessions amongst ourselves to try to see like, okay, what what sort of tests could have some potential for some application. How can we leverage, okay, for this particular application, what all processes do we need, like what is our in-house capacity? Can we talk to people who already have certain experience with certain fabrication methods? Can we talk first before just wasting time and trying things? So there's like a lot of to and fro that we go on by giving ourselves like almost like diverging, converging, diverging, and trying out a lot of different things amongst ourselves. And what's the most important is the ideations that I spoke about. It always happens with like a very diverse group of people. And that's where I find like the best ideas and novelty comes out of, is when you are sitting with a lot of people from different fields and you're talking about the same problem. Everyone comes with a certain kind of baggage of their field. Like as architects, as designers, you are taught or trained to think in a certain way, which is very different from how scientists and people from different fields are. But sitting in the same sort of space, discussing about the same issues together, always makes you feel like, hey, like I would never have thought of that. That's an interesting idea. Why not explore it? So that's where like I find that like the sort of beauty about transdisciplinary design, working together with different fields, is what brings a lot of joy to at least the work that I do. And regarding your second, can you can you repeat the second question?
Yeah, it was if you could have included additive manufacturing in the
Okay, yeah.
form project instead of cutting materials.
Yes. So again, so the whole I think I showed one of the charts where like there were different applications and there were different fabrication methods. Cutting definitely is an interesting process, which because you can cut it out of a flat sheet, it's way more accessible. Again, when you look at not just what happens in like the US, but even like the simple process of cutting, you can find it across like the world. Even though every part in the world might not have a robotic arm to be able to experiment with these kind of things, but a cutter is something that you can imagine is way more accessible. And based on cutting, you can see that it gives us a certain possibility of changing certain parameters. What you spoke about 3D printing as a process also offers a lot of interesting things where if we could 3D print these forms, now we can change the cross section of each and every fin. If we can change the cross section, how does that impact the deployment? Can we have more interesting forms of deployment? Can these cross sections be catered to resist certain wind flows or water flows? Like these can these cross sections be increased so that they are able to have more surface area or surface textures for certain things? Can these cross sections be modeled to have multi materials in it? One particular material might be taking care of all the structural loads. Another material might be more thin but have some sort of other texture. So all of this is possible in 3D printing, but not the cutting applications.
Yeah, I think that is well answered. I think it's clear. The advantage we have is, of course, of cross sections and different materials. When you add materials, when you're not bound to cutting one. Yeah, I'd like to open the discussion further to the students. Just one thing before that. I want to know if there's any possibility, and are you open for collaborations in any near time in future? It would be great to.
For me, that's one thing which I am in general very open about, because again, like I have been able to like expose myself to a lot of these like collaborative. See, all of these projects, it's very difficult to place them within one field, right? Like all throughout my time here, I have been collaborating with the School of Engineering, with biological engineers here, and for me, that is the beauty where I know that the idea of collaboration we can achieve more together. So throughout my time here, I have always been open to talking with people and sharing my knowledge, and also trying my best to sort of, like inform or educate people on this, like, hey, you should like talk to more people from different fields, help each other out.
Yeah, I think also, yeah, I mean, just stating that it's the best time to get into these things, and 3D printing as a process or as an invention by itself is open source, and I mean, so anyone from anywhere can benefit from it. So if you have any resources, or I mean, you've just given a link to one of your books. You mentioned one of your projects is on GitHub. Check that. But I mean, yeah.
Means I think one of the sort of like one of the biggest suggestion that I always feel that like that should happen more, especially like like I've done my undergrad.
Right?
So I start early, and again, having done my undergrad in Mumbai, right? Like I went to Balwant School of Architecture, and that's where I sort of got that sort of interest of like, oh, I want to know what's happening outside and what's happening internationally. And one thing which I see in general, like missing in India, is the sort of collaboration between, even if you're the part of the same university, right? But collaborating with one school with the other, like the School of Architecture or the School of Design can also talk to the School of Engineering because they're in the same university, but that still doesn't happen. And I think that is one thing which, I would be very much like, okay, this really needs to happen.
Yeah, I think we are getting there. It's something difficult, but yes. We should definitely engineering and design architecture. I mean, I understand what you said. That's how probably campuses in the West are. It's just one huge campus that gives you everything.
Yeah, miss, and especially even for me, it's like I see here like a lot of people within my group also are like having a lot of interesting collaborations, like from the School of Design, they're collaborating with like people in the neuroscience department to try to find out like, hey, we know exactly how to design spaces, but how can spaces change based on what you feel? And these are very interesting and like very new sort of topics, but right now you do get instruments which are able to measure certain biomarkers, and then you can try to convert those signals into certain changes in space. And what does that mean for the field of architecture? So right now it's like all the boundaries are blurring quite a bit. And from us, like that's like the interesting thing about like the blurring of the fields.
Yeah. Okay, then I'll pass it on to the students. I think there should have been a lot of questions by now. I would be curious if I was a student and something of this sort was presented to me. So yeah. Anyone? Okay, yeah. We have another faculty who has a question.
Yeah.
Yeah. Hi, Saurabh. That was really overwhelming. And I'm still trying to get my head around the possibilities that can happen. Just one question about it. So I saw that nozzles that you had for something called as a Janus nozzle and something else. My question is about this, that whenever suppose you are planning a design or design something with an element, every time you would have to design a new nozzle or a new kind of a thing. So, I mean, I'm just wondering if this can go on and on, right? So it's like a tool that you have, and that you have to design a tool first to get the design out of it.
So that's a very interesting sort of question, because it sort of takes me to the topic of rapid prototyping, right? Like right now, what I might have shown you in the presentation it was just like the final things, right? I probably had like, as a part of the process, 10 or 15 nozzles which were tried but failed, but didn't work the way we intended to. But that is like the beauty of rapid prototyping, where you make a lot of sketch models, like something that you can do very quick and just try them out. Like everything did not need to go on the robot. We could be just using small syringes, analog methods, to try to see how does this work. Like, and then at some point after we go through all of this process of rapid prototyping, and that's when the two nozzles were like, okay, now we know that these two nozzles can, like a lot of the tests that we did could be umbrellaed between two things. One is side by side and one is one inside the other. Even within each nozzle, we had to do a lot of tests to get the best, like what should be the inner diameter, what should be the outer diameter, what materials can we use. We even printed transparent nozzles to be able to see how the material would react when it goes from two sides and things. So it's a sort of like fun prototyping exercise for us before we hone down to the final nozzle.
So then the question arises that every time you think of a design, and so then you also have to design a tool for that, right? If you are going for something, it's like just what you showed, the analogy of the food getting production. Like you would have, for example, a pasta, fusilli pasta versus chakri, that thing that you showed. The mold will have to be designed first to get the design out.
So that's the truth, right? Like, and that's why we also end up creating parametric models, which makes it super easy for us that in the end, the only parameters I'm defining is what the start of my syringe is, right? And then what the end diameter is. And now I can change the parameters and play with a lot of different things. And I can, because everything is parametric, it's very easy for me to get the 3D file of it and quickly print it and test it out.
Okay. Just a quick another question before I quit.
Sure.
There's too many questions I have, but I'll leave it open to the student as well. And that is, you showed that machine. Does the same machine work for different materials like say clay, concrete, plastic? You're talking about printing,
the extruder, right? Yeah. So it is sort of a machine which is quite flexible. So I can say that machine can be used to print a lot of viscous materials. It can be, so you can print concrete with it, you can print clay with it. Different materials have different sort of, like, a lot of people print concrete because it's simple. Concrete does not shrink. And that is why we feel there's more opportunity with clay. A lot of people hate it because there's such a change in shrinkage that the tolerances is very difficult to determine.
Yes.
And that is one of the reasons why there's no mass adoption of ceramic. In like customized ceramic, 3D printing is not massively adopted yet. But in contrast, you see a lot of people are 3D printing concrete houses.
Yeah. This is really overwhelming. Thank you so much for this wonderful presentation.
Thank you for the questions.
Thank you.
Yeah, so any students, please, come forward and
Hi, Saurabh. I'm Ainsley Lewis, the Dean of the Master's Program at KRVIA.
Hello.
I have a question for you. The thing is, whenever we look at this kind of processes, which you actually showed, actually fantastic presentation. It is excellent. I wish there were more students who were here because we're very keen to kind of get this connect with the students to kind of use digital kind of tools for their design, and rapidly they can make iterative models, etc., etc. So anyway, it's picking up thanks to Dharmesh, who's here, and how the lab has been set up. But when we actually look, so my question to you is, when we actually look at all these kind of processes which are done, whether it's at ETH Zurich, or whether it's an IARC, or whether it's done at MIT Fab Labs, etc., they always end up, at least for architecture, they always end up being one kind of solution which is there. Now, looking at the context of Mumbai or India for that matter, I mean, this could easily be used to rapidly manufacture various things like housing, like, for example, during the Industrial Revolution. I mean, this idea of modular furniture, modular homes, modular components to put up homes was a very important kind of a thing. How do you look at this this kind of process, technique, design with respect to India and the possibilities of using it in maybe answering the issues of housing for all in India?
I think the whole idea of like 3D printing, like I feel like you hit upon that, where like in terms of looking at affordable housing and how can we make these things very easily, very quickly. And one of the biggest sort of the interesting fact about 3D printing is that there also needs to be a lot of sort of research and investment in the material itself. And I think it has a lot of potential in a lot of different contexts. Again, like based on the context, be it Mumbai, there might be certain things that can be changed. Like I personally feel that ceramic has a lot of potential, where again, there's a lot of people who are using the adobe in certain areas, processing it locally on site and putting it inside this sort of gantry kind of printer and be able to make houses. And again, being from India, we also have a lot of vernacular architecture, which has been in the past done through those methods. And I feel like there's something very interesting where we look at and study the vernacular architecture and see how that can be combined with all of these emerging and modern technologies. I see there's a lot of potential in these things. I also see, being from Mumbai, that looking at all the universities which you mentioned, ETH Zurich, IAC, ICD, and all of these, they have tremendous amount of funding to be able to make all of this like live scale prototypes. And I feel like that's something which is only possible through partnerships of industry and academia. And I feel that more of that needs to happen. And if that is possible, then definitely like full scale prototypes and things can be tried and tested. And I see like Mumbai, India having a lot of potential to explore a lot of these things because we have such a rich backing of vernacular like art and techniques, which might be interesting, like the old art, the old vernacular style mixed with modern technologies can give us something really novel.
So you're planning to come back to India?
For me, I'm still debating that. Like for me, that's also the beauty where like I feel like I would be my best case scenario is to be acting as a bridge between what's happening here and what's happening there, and to be able to sort of link both of these things together. That's my ideal case scenario that I would want to do.
Okay. Thanks a lot. Looking forward to meeting you when you come to India.
Yes, I would definitely connect with you once I'm there. I definitely, I usually come once a year there, so yeah.
Yeah. Okay, thanks.
Thank you, everyone, and thank you, Saurabh, for this extremely informative presentation. With this, we would like to end today's discussion. Thank you.
Thank you so much for inviting me, and again, thank you for your attention.
Thank you. Bye-bye.
See you. Thank you, Mamta.
Yeah, thanks, Saurabh. That was fantastic. And we look forward to some kind of collaboration. Yeah, I would just love to have you here
I'm very open, and I think
next
I
time
shared
that you're visiting.
I shared my email address and everything with you, so feel free to connect with me. And at any point, like I'm more than happy to help get on a call, or if you want to know more about anything, these processes and technologies, I'm very open. Yeah.
Cool.
Yeah,
Thanks.
thank you so
Bye.
much.
Bye.
See you.
Bye.
Thank you. Bye.